Good morning, everyone. So, we will be beginning the course on fundamental applications and modelings of membrane based separation processes. Initially, in this lecture, what we will be covering will be defining the separation processes, and then we will be looking into fundamentals and various definitions of introduction of the membrane separation system. So, we start with what a separation process is. Let us look into definition of a separation process. In a separation process, there should be a feed stream, then there will be some agent will be giving input to the system between feed stream and the product stream, and the external agent can be either energy or matter. Okay. So, one example of energy is distillation, where energy is given in the form of heat energy supplied by a reboiler. So, reboiler supplied the energy and the feed stream is divided into the various product streams. In case of, let us say, coagulation or adsorption, it is the external agent is matter. We add an external agent to effect the separation. So, input of energy or matter is essential for effecting a separation process. Now, let us look into the extent of separation, how we define extent of separation between two species I and J. I and J are two species. Alpha I j is defined as x I 1 divided by x j 1 divided by x I 2 x j 2, where 1 and 2 are two process streams. Okay. So, this is also known as the separation efficiency. So, I and J are two species, 1 and 2 are the two process streams. So, if alpha I j is equal to 1, then there is no separation occurs. If alpha I j is less than 1, then stream 1 is concentrated in J and stream 2 is concentrated in I. If alpha I j is greater than 1, then stream 1 is concentrated in J and stream 2 is concentrated in stream 1 is concentrated in I and stream 2 is concentrated in J. So, by looking into the value of alpha I j and the composition of the product stream and the feed stream, one can identify which stream will be rich in which species and which stream will be lean in the other species. Now, let us look into the driving force of any separation process. the driving force of any separation process is gradient of chemical potential. Now, all of you must know about the chemical potential. If you forget, you just brush up your idea of basic thermodynamics. Chemical potential will be a function of, if you remember, pressure, temperature, composition and electric potential of the system. Typically, in an uncharged system, we will be having only these three independent thermodynamic properties which will be influencing chemical potential. Now, chemical potential is not a directly measurable properties, only pressure, temperature, composition, etc. are the directly measurable thermodynamic properties, and there exist relations like Gibbs-Duhem relationship by which these independent properties will be related to chemical potential. So, therefore, if there is a change in pressure, temperature, composition of the system, that will lead to a gradient of chemical potential, and that will be finally leading to separation of species. Okay. So, basically there may be a combined effect of this, any of these thermodynamic properties, or if any one of them, any two of them, if any all of them will be changing, that will be affecting the gradient of chemical potential, leading to separation of the species. Okay. So, once that is identified, let us go to the definition of separation processes. There are basically two broad categories of separation processes. One is equilibrium governed separation process, another is rate governed separation processes. In equilibrium governed separation processes, the equilibrium relationship, equilibrium existing between feed and product stream will govern the extent of separation. So, therefore, there will be a maximum limit at a particular temperature. So, there will be a maximum limit of separation that is that can be attained or exists in equilibrium governed separation processes, because the composition of a particular species will be following an equilibrium relationship in the feed and the product stream. So, one cannot go beyond that maximum composition. So, there is a limit existing between in case of equilibrium relationship, equilibrium based separation processes, and all the basic separation processes that we have studied in third year and fourth year, they are falling under this category, equilibrium governed separation processes. So, what are the examples? Distillation, absorption, adsorption, drying, extraction. There are many others. So, basically these are some of the examples of equilibrium governed separation process, and in any process engineering of typically appearing in chemical engineering, the separation is an integral part. So, one has to go for the product separation. Even if you have a reactive system, there will be product of several species that will be coming out after the reaction, and some of the products will be desirable, some of the products will be undesirable. One may have an aim to maximize a particular product out of various other products existing in the stream. So, therefore, one has to go for a separation process in the downstream, and based on the system performance or based on the your objective, one has to take recourse to the either equilibrium governed separation process or rate governed separation process. Now, let us see what are the rate governed separation processes. The rate governed separation processes are basically those processes where rate of transport of a species in the system governs the separation extent of separation. For example, most of the membrane based separation processes, they fall under rate governed separation processes, membrane based processes. Okay. For example, reverse osmosis, ultrafiltration, nanofiltration, microfiltration, all pressure driven separation processes, membrane based separation processes, they fall under the rate governed separation processes. Now, so that is the difference between a equilibrium governed separation process and rate governed separation process. So, effects of operating conditions are quite crucial in rate governed separation processes. For example, if you can maintain all these separation processes that I have given an example, they are basically the pressure driven separation processes. So, if we increase the major driving force, that is the pressure drop across the membrane, if we increase this driving force, then the rate of the species will be altered. So, one can go for a higher throughput or a higher extent of separation by controlling the operating conditions, or vis-a-vis by controlling the rate of transport of the species through the in the process or in the system. So, that is the difference between the equilibrium governed separation process and rate governed separation process. Now, I think we should directly get into the membrane based separation processes. So, in membrane based processes, first we will be looking to what is the definition of a membrane. Membrane is defined by a phase that gives a preferential transport, leads a preferential transport of a species among many. So, if there are number of species present in the feed stream, then a particular species will be preferred to be transferred to the through the membrane. Therefore, the product stream will be enriched in that particular species, and the and in terms of other species it will be of having lower concentration. So, that is the definition of membrane. Before going into the fundamental transport mechanisms of the membranes and categorization of the various processes, first look into what is the typical casting process of a membrane, casting of a typical polymeric membrane. I will be mostly concerned and concentrated on polymeric membrane, because these membranes can be of two types. Either they can be polymeric, they can be inorganic, they can be organic like polymeric, they can be inorganic like alumina, ceramic, etc. Now, there are advantages and disadvantages of both types of membranes. For example, the polymeric membranes, the basic polymer, the base polymer by which the membrane is formed, either polysulfone, polyacrylonitrile, polyurethane, PVC, polyvinyl chloride. There are blends, cellulose acetate, that is the starting material of membrane, polymeric membrane, their combination blends, so on and so forth. Now, the major advantage of the polymeric membrane is that one can really control the pore size of the polymeric membrane to a fine extent. One can control the pore size up to the range of angstrom, which will be used for separation of monovalent salts. On the other hand, this polymeric, so that is the major advantage. That means pore controlling can be achieved. Fine pore controlling can be achieved. On the other hand, these polymeric membranes, they cannot withstand high temperature. And what is the very high temperature? Typically beyond 80 to 90 degrees centigrade. So, therefore, if you have a process stream of high temperature, you cannot directly get into the into the membrane system. One has to go through a heat exchanger, bring the temperature down, and then direct it into the membrane based in the process having the polymeric membranes. On the other hand, in case of inorganic membrane, the problem is not that much. In case of inorganic membrane, one can really go to a process, one can handle a process stream at very high temperature. At high temperature, and what is a typical high temperature? So, anything 250 degrees centigrade, 500 degrees centigrade, it should not be a problem. It has a thermal stability, high thermal stability, but the major problem of the inorganic membrane is that the pore size control at lower pore size, like in less than micron, is very difficult to obtain. So, pore size control to lower range. What is the lower range? In the range of angstrom and nanometer is not possible. So, therefore, for the inorganic membranes cannot go below the micron sized pores, for example, for the microfiltration. So, these are the difference between the organic and inorganic organic and inorganic membranes, and then we will be looking into the membrane casting, various steps of membrane polymeric membrane casting. First, we take we select polymer, dissolve it in an organic solvent. In an organic solvent, and what is a typical organic solvent? Typical organic solvent is DMF, that is dimethyl fluoride, DMSE, DMSO, dimethyl sulfoxide, and then acetone. So, these are various typical organic solvents by which polymer is dissolved. Once we select the polymer composition and the solvent, then it will be dissolved in the solvent. What will be resulting? A resultant will be a viscous solution, and this solution will be continuously stirred or sonicated, so that there will be no agglomeration of the polymeric material into the solution. So, it will be producing a homogeneous solution. So, once the homogeneous solution is done, actually the homogenization of the solution is kept on, should be continued, so that there will be no dissolved air bubble present into the solution. Otherwise, if you would like to cast it, then there will be defects that will be appearing in the polymer film, and which is not desirable at all, because that will be disrupting the continuity of the polymer film, and it will deteriorate the performance of the membrane. So, once the viscous solution is done, then it is cast on a third step is the viscous solution is cast on a polyester fabric, non-woven polyester fabric, by a casting knife, which is also known as the doctor's blade. So, once it is cast, then it will create a very thin film of polymer. Now, what is a typical casting knife? A typical casting knife is a mirror polished cylindrical object having the square or rectangular cross section at the end, and the typical cross section looks like this. So, when you place this cross section on a surface, and all these surfaces are calibrated properly, that if you just turn it, then it will be creating a gap, let us say 50 micron between the surface and the polymer film solution. And if you just turn it once again, so that one can realize, let us say 100 micron. So, since there are 4 surfaces of this square or rectangular cross section at the end, one can realize at least 4 thicknesses of the casting film, let us say 50, 100, 150 and 200 micron in the same doctor's blade. So, therefore, using the doctor's blade, same doctor's blade, one can realize 4 thicknesses of polymer on the polyester fabric. Then there will be given an evaporation time. What this evaporation does? During this evaporation, the solvents will be evaporated through the polymer film. During their evaporation, the fine pores are formed into the polymer matrix, and typically this evaporation time may be from the in the order of second to minute, 1 or 2 minutes. Once that is done, then it will be immediately put into a gelation bath. What is a typical gelation bath? Typical gelation bath is basically an aqueous solution, let us say water. Water being an antisolvent, it is a bath of antisolvent to the polymer. Once the antisolvent comes in contact with the polymer film, immediately the phase inversion takes place. So, this is also known as the phase inversion technique, and the polymer film gets solidified and transfer from the liquid stream, and the membrane is formed. Polymer film is solidified, membrane is formed. There will be exchange of solvent and non-solvent from the polymer matrix, and solvent from the polymer matrix and non-solvent from the aqueous stream. Because of the concentration gradient, they will be immediately exchanging. The solvent will be coming out from the polymer matrix into the gelation bath, and the non-solvent will be going into the polymer matrix from the gelation bath. So, therefore, whenever the non-solvent will be getting into the system, into the polymer matrix, immediately they will be forming bigger pores, and the pores will be formed. So, this will be creating the pores into the membrane matrix, and this solvent non-solvent exchange is known as the demixing. This demixing can be 2 types. It can be a quick demixing. So, in case of quick demixing, the exchange of solvent non-solvent will be very quick, and it will be leading to a a very dense polymer matrix. On the other hand, if the solvent and the demixing is delayed demixing, then it will be forming a larger pores into the membrane matrix. So, by controlling the extent of mixing and demixing, one can really control the pore size distribution. So, what are the basically the various controlling factors of pores? Okay, once the membrane is kept in the gelation bath and is formed, then it is taken out. Then it is taken out from the solution, and it's dried, and once it is dried, then it is stored either in distilled water or into a preservative solution, so that there will be no microbial attack on the polymer film or the membrane film. Okay. So, once by controlling the demixing, quick demixing or delayed demixing, one can really control the pore size of the membrane. Hence, the various let us just tabulate various affecting factors, controlling factors, which can be essentially control the membrane pore size. First factor is composition of polymer. If you take a 10% polymer solution, then you will be landing up with a particular membrane. If you take a 20%, it will be landing up probably a denser polymer matrix. So, composition of polymer solution. So, basically I am talking about the composition of the casting solution. Second is nature of the polymer. Of course, selection of polymer is very important. If you select a polyacrylonitrile membrane, you will be getting more porous membrane, for example, microfiltration membrane. If you select a polysulfone membrane, then one will land up into an ultrafiltration membrane, like that. So, nature of the polymer is very important, composition of the casting solution is very important. Third one is the selection of solvent. Now, depending on whether you will be selecting DMF, DMSO, DMSE or acetone, the pore size distribution of the membrane will be altered. Fourth one will be the nature of additive and their concentration, nature and concentration of additive. One can use various pore forming agents, they are also known as the porogens. These pore forming agents are polyethylene glycol, polyvinyl pyrrolidine, and there are various molecular weights of polyethylene glycols are available. There are various molecular weights of polyvinyl pyrrolidine are available. So, one can alter the concentration of these additives, the molecular weight of the additives, and these pore forming agents, they forming pores into the membrane surface and can alter the pore size distribution. The nature of the anti-solvent is also important. That means, nature of the gelation bath, whether you are using water, whether you are using water PEG solution, whether you are using water DMF, water solvent mixture. So, that will be very important. So, if you use pure water, the transfer demixing will be more. On the other hand, if you use a solvent anti-solvent mixture, then the concentration gradient of the concentration gradient that will be driving anti-solvent into the polymer matrix will be less. So, by that way one can control the pore size distribution. Also, another important point is the film thickness, because if you have a film of shorter thickness, then the resistance, the hydraulic resistance offered by the membrane against the solvent flux will be less, and one can expect a higher throughput of the process. If one goes for a larger film thickness, then the resistance against the solvent flux will be more, and the resultant throughput will be less. So, film thickness is also an important factor. Then next one is the temperature of casting solution. As well as temperature of gelation bath. As we have already discussed earlier, that temperature is one of the controlling factor to alter the gradient of chemical potential. So, if you alter the temperature of the casting film or the gelation bath, that will be again really controlling that will be really controlling the demixing process of solvent and non-solvent, resulting into a particular pore size of the membrane. So, that will complete the membrane casting process and the basic fundamentals of the behind the any separation process. So, we will be taking the next class on different factors of different properties of the membrane, which will be very important, and we will categorize the various membrane separation processes. Thank you.